Okay, we get to a section called the definition of vector components. They're kind of looking at what does it take, how do we talk about dividing a vector up into like its x and y components, and we learn that there's something called the projection of u onto v. I need to add a little something here that I couldn't really type. There needs to be a small v right there, okay? Now, here's what's going on. They're setting up kind of like a perpendicular set of vectors, and you could look at it kind of like what would happen if I put this on the coordinate grid and put, looked between 0 and 90 degrees in quadrant 1 if it's an acute angle. If it's a obtuse angle, you can look in the book for that. If it's an obtuse angle, you're actually looking at quadrants 1 and 2. But we'll talk about the acute just to get it a little bit more in our heads because it's kind of a weird thing to understand. Okay, so you got these perpendicular lines, and I drew those in black, W1 and W2, and then you've got this vector U. Now, W1 should actually end here. I should put the arrow for W1 right here, and just ignore that. What they've done is they've taken a vector U, so you just got some vector, you put it in this little scheme like it would be on a coordinate grid or something, and you kind of come down here, and what W1 ends up being is like I guess you could call that maybe the X component, if you want to think of it that way. And W2 up here would be kind of like your Y component if you were looking in the grid, if you're looking at a coordinate grid and you had put this on there, okay? So that's what W1, W2, use just the vector, and they're just saying you've got these perpendicular vectors, W1 and W2, kind of like a coordinate grid, okay? Now, you always kind of make W1 parallel to the vector. W1 is parallel to V. So you've got, basically, actually you have two vectors. The blue are the vectors that I've drawn, okay? So you got the vector U, we've looked at its X and Y components, and we've got this smaller vector V. And they might ask us, what's the projection of U onto V, okay? Let's see, did I write that here? The vector W1 is the projection of U onto V, okay? So basically it's like if I were to take this, it's almost like look at it as the shadow, I guess. What if the sun, here's a way to look at it. What if the sun were sitting up here and you had this vector and it was like a board or something. You represent it with a board and it's sticking up out of the ground like this, and it were to shine down, and then where would the shadow of that lie? It would lie on W1 would be kind of the shadow of the vector U on vector V. So you basically, you got these two vectors. You line up the shorter vector, if it's acute, underneath the bigger one, and you kind of put that shorter vector along your x-axis. It's almost like you're taking it and just turning it in your place in there. And we're asking what would that shadow be, W1, okay? So W1 is kind of like, if you think of it in terms of an illustration of a board and a sun shining down on it, it would be the shadow of U onto V. And it would be equal to W1. Let me go ahead and make the end of W1 black here just so we can tell there's a black vector there and a blue vector there, okay? Okay, now, there's a way to find this, and we're going to get a formula for this W1 in a minute. Well, actually, let me go ahead and write it here. If I want to find that projection of U onto V, which is equal to W1, the shadow, what we would do is we would take the dot product of the two vectors and divide that dot product, remember it's just a number, by the magnitude of vector V, which is that smaller vector down there, right? And actually, I don't know that V has to be smaller. There's nothing in the definition that said V has to be smaller, so this could be in reverse. U could have been shorter than V. It doesn't really matter because this formula is going to work either way. So you don't necessarily, I kind of misspoke when I said you put the shorter vector underneath. You could flip these and this process would be the same. Anyway, what you have to do is take the dot product, you take and put it on top. Then you take the magnitude of vector V, which is the one that you've lined up with your x-axis, sort of, if you want to. Think of it that way. So you're going to take that number that you're going to generate, and then you're going to multiply it by vector v. Okay, so v is the vector. So you got it. It's basically, it's a scalar. This thing in the parentheses, this fraction, just gives us a number. It's like a scalar quantity, and then we multiply that by vector v. So when you get done, you're actually going to have another vector. It's going to have two parts, kind of like the x part and the y part, though we really don't talk about vectors that way. It's the best analogy I know to give you, okay? So what we can do, if it's acute, this is what we do. If it were obtuse, we'd have, let me draw a little obtuse, just to talk about the obtuse case. What if I had vector v there, and what if vector u had come out over here? That red one we'll talk about it as vector u. Let's say in the acute case we had that. Then what we would have going on is that W1, I would draw, okay, I'm going to make this really, really tiny over here just so we can fit it on the screen. But vector W1, the projection would actually be, let's see if I can't draw it over here, this thicker of the two red lines there. That's where it would end up if you wanted to see it in a picture, and your theta would actually go here, okay? It would be talking about that angle. So you can use this formula to do find the projection of one vector onto another vector. You might want to do that if you were talking about forces, finding a force on something. You may have to do some kind of projection for that. They're different applications where you might use this, so we'll get the idea down first. Okay, so here's an example of how we could decompose a vector into its components using the information we talked about on the first slide there. Find the projection of a vector u, and they give us its coordinates, onto v, and they give us its coordinates. It would be a good idea to sketch this. Let's say that vector v is 6, 2, and that's right. Let's say 6, 2 falls about right there, okay? So I'm going to draw that in a color just so we can kind of keep some things straight. That's vector v. And I'm going to go ahead and take this line, my coordinate axis. I'm really thinking of this as a coordinate axis, though really you could do this anywhere. It wouldn't have to be moved back to 0, 0, but it's easy to think. It's easier to think about this way, so I'm going to discuss it this way because it's even easier for me to understand it this way. So if that's vector v, and then I want to have vector u. So if this is 6, 2, let's say that 3, negative 5 was here, okay? And let's say this is vector, I'm just approximating things just for us to have a picture. This is vector u, okay? Now, if I want to break this down, what I have to do is make W1 parallel to one of the vectors. And so if you look, what we do here is we're going to say, I'm going to draw W1 here. It's really sitting on top of this red line, but I'm going to draw it like this, okay? And W1 is parallel to vector v. And I'm going to write it like that, okay? Now, looking at this visually, I've got to have the perpendicular vector to W1. So maybe I could draw W2 from W1 like this. I'm going to take it and I'm going to join it to the endpoint of u. And I'm just going to drop a perpendicular line down like this, okay? And so this vector would be W2. If I want to find out what W1 is, the projection of u onto v, so really what's happening is u, I probably should have drawn that a little bit further over here, W1. U ends here, and if I were to kind of think about drawing perpendicular line here, okay? Maybe the sun would be down here if you think about my analogy, or down here somewhere, and it's shining on you. Where's the shadow W1 going to be? I'm going to make it a dark green, okay? So let me make W2 be this dotted line instead of the other line I drew. I can't really get rid of it without messing up the whole picture. So W2 is this dotted line, okay? That's where it would hit. How long is W1 then? How long would W1, if I make the endpoints of it big, would be kind of like from here to here. Okay? It's on V. We're projecting U onto V, so the shadow always ends up on V. It starts at U, ends up on V, okay? So what would that be? We can use the formula now. W1, which is the shadow, I'm going to put shadow, is equal to the projection of U onto V. U onto V. And so we could figure this out. It's a vector. What is this vector W1 here? Okay, how I do it, remember, I've got the formula. U dot V over the magnitude of V squared. Hard to read that, but hopefully you've got the formula down from the other page. And then we multiply it by vector V. Okay, so what is U dot V? Let's come down here and I'll use some different ink and we'll do some work so we can just plug everything up into the formula up there. U dot V is the cross product, and basically for the cross product we multiply the 2x parts together, 3 times 6, which would be 18. And then we add in something, and the thing we add in is what we're going to do is we're going to multiply the y parts together and add that in. So 2 times negative 5, I'm looking here and here, 2 times negative 5 is negative 10. So the 18 plus negative 10 would be 8. So the dot product is 8. I'm going to put that on top of my fraction there. That's this. I'm going to highlight in blue there. Now another piece that I'm going to need is the magnitude of V. And the magnitude of V, remember, is the square root of the 2 parts of V squared and added together. So it would be square root of 6 squared plus 2 squared. That would be the square of 36 plus 4, which is 40. And I could just put that as the square root of 40 if I wanted to. Because what am I going to do with it? I want it squared. So square root of 40 squared is going to end up being 40 in a minute. I'll simplify that in a minute. Now vector V. Let me kind of take vector V and circle it up here. Here it is. It's 6, 2. 6, 2. It has 2 parts to it. We're going to have a vector as our answer. Now 8, now let's work this, and I'm going to go draw a line here just so we can kind of go back up here and separate the little side work I did from the main work. And I'll write in black now. 8 on top, square root of 40 squared is just 40. That's going to reduce to 1 over 5, so I'm going to go ahead and reduce it, and I'm going to multiply that by 6, 2. And so my answer is going to be 6 over 5 and 2 over 5. That's the projection of U onto V. There's my answer for that part. Okay. Now, they want to know, W1, they want to now know the vector U as the sum, okay, vector U, they want it as the sum of the 2 orthogonal vectors, one of which is the projection of U onto V. Okay, so remember vector U is here, and vector U was an original vector. They want us to write it in terms of the sum